Hello. This is like my third take now, so hopefully this one works. We're going to talk about some theorems, some tests, and some vocabulary. So, starting with extreme value theorem. We have a function on the closed interval. It has a function on closed interval has an absolute maximum and an absolute minimum. So, that's literally what that is. It's not showing like it's not asking you to usually solve anything with that. It's just a concept that you need to know. Have a little nice graph to help you visualize. So let's say our function looks like this. Oh wait, no arrow, because it's a closed interval, right? So this is A, and this is B. So this is our closed interval here. Essentially, if it's closed, you're going to have an absolute maximum and absolute minimum. Whereas if it weren't closed, you may only have local maximums and minimums. But on a closed interval, you absolutely have a absolute max and min. So if we just look, we can see the absolute maximum is right here. Max. Absolute max. Because that is the highest maximum on the function. So we have another maximum. Oh, shoot. We have another maximum here, but that one only reaches to this y value. So that's how we know that this point is the absolute maximum. And then here is our absolute minimum. See here we also have a minimum since it's it's a minimum, but it's not as far down as this minimum is. So that's how you know which one's absolute and which one's the not absolute. Let me get rid of these dotted lines actually. Oh, sure, I keep doing that. Absolute min. So when you would use this theorem is for something like the candidates test. So the candidates test is you just testing every single critical number and point of potential extrema to see which one's the absolute maximum and minimum. So that means you would test these points of extrema and you would test these points where you have extrema and the endpoints where you could have extrema. And all you do is you just like line them up in a table. So this is your x values. So it would be like x value here, at B, like here, and at A. And you just put them all on this table. Oops. Like blah 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 blah. And you plug them into the function to see what y values they get. And whichever one has the smallest y value, that's your absolute minimum. Let's say it's that one. And then whichever one has the highest y value, that's your absolute maximum. So that's basically the candidates test. It's just for finding absolute minimums and maximums. Okay, let's get rid of this. Okay, mean value theorem. So there's two conditions that have to be met before you can use mean value theorem. First is that f is continuous on the closed interval. And the second is it's differentiable on the open interval. And a way to remember that is if we use this as an example with our endpoint, this endpoint here we can't find the derivative of, because a derivative is the slope of a tangent line, but this point here has tangent lines here, 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 here. Essentially there's infinite number of tangent lines, and we obviously don't know which one to pick, right? So we just don't include the endpoints. So if those two things are true, then you know this is true. So this is saying you should recognize this as your slope that you've learned since you are a little small child. y2 minus y1 over x2 minus x1. That's what this is. So it's saying that the slope between 2 points is the same value as some c that you plug into the derivative. So that c that you plug into the derivative is going to give you the same slope of the tangent line as your average rate of change, your slope. So if we draw our graph, oh, ugly. And here, let's say our graph looked like this. Very simple. And we have a point here and a point here. So we have this point and this point. So let's call this A, f of A. And then this one can be B, f of B. So this slope between these 2 points is the same as if you had a C somewhere. Let's say about there. That's not very close. Let me try that again. Yeah, that's close enough. If this point C, what was I saying? But you see how these are parallel? I'm going to draw those arrows so you know they're parallel. Wait, put it here. So they're saying that you have some x value c that you can plug in to the derivative that will give you the same derivative as the slope between these 2 points. So that's c f of c. So that's what mean value theorem is. You have a slope between 2 points. There's some value c on this function where you put this c into the derivative and you get the derivative and you get the slope of the same slope as the slope between these 2 points. Okay, intermediate value theorem. One condition, it has to be continuous on the open or the closed interval. And you have these 2 y values. Remember that f of something is just same as a y value because this a and this b are x values that you plug into the function. And when you plug an x into the function, you get a y out. So the only thing is these y values do not equal each other. And you also have another number n that is in between these y values. So you know n is a y value as well, okay? So if you have n in between the y values, then there's a number c, which is an x value, that you can plug into the function that will give you that y value n. So I know that was a lot of y value, x value, so we're going to draw a graph to show. Let's put it right here. And here's our graph. Very simple. Okay, so I'm going to have some x or some y value here. This is going to be my f of a. And then I'll have some x value over here. Oop. This is my f of b. So these are my 2 y values from here. From here. Oh, And then I have an n that is in between these 2 y values. So let's say that n is like right here. Oops. Then there's a number c. Oh, and I forgot to mention, but this is a and this is b. Because you plug in the a into the function to get the y value. You plug b into that function to get the y value. So, And now there's some number c that we can plug in that will give us this n value. So that means c is like right here. C. And plugging in c will give us n. So this is us plugging in c. So this shows that you're plugging c into the function, and that will give you this n value. So that's what intermediate value theorem is. It's just saying you have two y values, you have a y value in between them, then there's a c that will give you that y value that's in between them. There's some xc that will give you that y value that's in between them. So let's just highlight this so you can differentiate it from everything else. Okay, next we're going to talk about critical numbers. So critical numbers are points where you could potentially have extrema. You don't know for sure, but because you have to test it, but you know where to test based off of what your critical numbers are. So to find a critical number, you have to set f equal to 0. So you have critical numbers where f prime of x equals 0, or where f prime is undefined. So those are places where you have critical numbers. And that relates to our increasing decreasing test here. So if f prime is positive, then f is increasing. If f prime is negative, then f is decreasing. That's just the increasing decreasing test. So to find increasing decreasing, we have to find the points where there are critical numbers, aka potential changes in the graph of f, and then we plot them on this number line to see whether it is increasing or decreasing. So this is just the example that I used. I didn't want to erase it and write it all again, so I'm just going to walk you through it. So I just took the derivative of all of these. You can see power rule, so you bring the 4 down to the front. 3 times 4 is 12, and then you subtract 1, so x to the 4th becomes x to the 3rd. Same thing here, 3 times 4 becomes 12, x to the 3rd becomes x squared, 2 times 12 becomes 24, and then x squared becomes x, and the derivative of any constant is a 0. And then what I did is I saw each of these had a factor of 12, so I took out a 12 from everything, and I saw everything had a factor of x, so I also took out an x from everything. So I was left with this, which you can factor into x minus 2 and x plus 1. So remember, these last two values have to multiply together to become this value. So negative 2 times negative 1 is negative 2, so that's fine. And then they have to add together to become this value. Remember, there's an invisible 1 in front of that x. So negative 2 plus 1 is negative 1, so that checks out. And then we use zero product property to separate everything and find the values of our x. So this goes here, here, here. And from this, we divide our x over there, we get x equals 0. We move our 2 over there, we get x equals 2. We move our 1 over there, we get x equals negative 1. So now these are our critical numbers. So what you do with them is you put them on a number line. And remember, you always want to label your number line so then you don't lose points for that, because otherwise it just looks like a random number line in the middle of your paper. And to know what interval we're on, we have to look at this function, f of f prime. So f prime is a polynomial, meaning it's just made up of a lot of terms together and with various degrees of x. There's 2, 3, 1 here. So that's a polynomial. And polynomials are all their domain is all real numbers. So they're continuous everywhere. So that's why this interval goes from negative infinity to infinity. And then we just plug in our, plot our critical numbers on the number line. And you just pick a number within that interval and test it in f prime. So I chose to use this version of f prime because it has everything like separated out for me. So it's easy to just see the sign as whether it's positive or negative and then move on, because that's all we really care about. We don't care about what the value is, we only care about what the sign is. Now, you want to be careful when you're choosing, because it just has to be some sort of f prime. But generally the one that's factored, sometimes you can divide, my goodness, divide like this negative 12 over there to get rid of it. And then that would change the value of f prime. So you want to make sure you're using just the natural f prime as its like original value. But this one, I didn't change anything about it, I just factored it so I can use it to plug in and test points on this interval. So I'm just going to plug in a negative 2. A negative 2 into this is negative. And we get negative and a negative. So 3 negatives, that makes a negative. If I plug in negative 0.5, I'm going to have negative, negative, positive, so that becomes positive. I plug in a 1, it's positive, negative, positive. So it comes out to negative. And then I plug in a 3 here, so it's positive, positive, positive. Everything's positive, so it's positive on that interval. And then, if the question were asking, on what interval is f of x increasing and decreasing, then all you do is answer the question first. F of x is decreasing on this interval. See how these ones are, these intervals are the ones with the negative, so boom. And then I wrote this is like a short way to write and, but you can write the word and it means the same thing. So this is your answer, but then you also need a reasoning. So this is your reasoning. Because f prime of x is negative on those intervals. So that's you bringing in the increasing, decreasing tests. And then you just do the same exact thing. F is increasing on these intervals because f prime is positive on those intervals. Very simple. So that's increasing, decreasing test. And then we can relate it to the first derivative test. So what the first derivative test is, you have a critical number, and if the sign of f prime changes from positive to negative at that critical number, then you have a maximum. If the sign of f prime changes from negative to positive, then you have a local minimum. So to help you visualize this, if f prime is positive, that means the function of f is increasing. And then if f prime is negative, that means the function of f is decreasing. And it changes at this point c. This is the function f. So that means you have a maximum here, because you see how it's like a hump? That's your maximum. And then if f prime is negative, that means f is decreasing. And then if f prime is positive, that means f is increasing. So right here is where it changes at c, and this is a minimum. And this is the graph of f. So let me just highlight this. Graph of f, maximum, f, minimum. Okay. And now we're gonna see how the first derivative test uses f prime as well. So that's why it's kind of connected to the increasing, decreasing, because you want to use this graph from the increasing, decreasing test to find the local maximums and minimums. So all we do is look here. We change from negative to positive at -1 and negative to positive at 2. So that means at -1 and 2 we have minimums. So you answer the question, local minimum at x equals -1 and 2. And your reasoning is you're just citing this because it changes from negative to positive, because f prime changes from negative to positive. So f prime changed from decreasing to increasing. Okay. And then here you have a plus, and then turns into a minus at 0. So that means it went from increasing to decreasing. So that's a maximum. So you answer the question, you have a local maximum at x equals 0 because f prime changes from increasing to decreasing. And that's how you answer questions about where f has a local maximum or minimum. Okay, next we have concavity. So concavity is essentially the same thing as like this increasing decreasing test, except you're using the second derivative. So if the second derivative is greater than 0, then f is concave up. If the second derivative is less than 0 or negative, then f is concave down. So you're going to do the exact same steps as the increasing decreasing test. So if you know how to do increasing decreasing, then you know how to do concavity. The only difference is that this isn't f, this is like f double prime. But you still you factor it and you still put it, you find critical numbers, put it on the number line. And you would just call this like sine of f double prime. And you still find the signs of the intervals. It's all exactly the same, just for double prime. And then where it's positive, you have concave up. And then where it's negative, you have concave down. Okay. And that leads us to point of inflection. So a point of inflection is where concavity changes. So that's more similar to like the minimums and maximums, where the f prime changes. Now we're talking about where f double prime changes. So I'm going to draw a little graph to help you visualize. Here's our graph, very small. Let's say this is our function. Oh, that's kind of ugly. Oh, that's much better. So here you can see the graph is concave down, and over here it's concave up. So that point where it changes, so like roughly about right here, that is our inflection point. That's the point where concavity changes. And you find that basically the same way you find minimums and maximums. So we change from concave down, if this was like f double prime. Change from concave down to concave up, so you have point of inflection there. Change from concave up to concave down, so you have point of inflection there. Change from concave down to concave up, so you have point of inflection there. That's how you would read that. Oh, and a side note is that when you have concavity down and you're like trying to estimate the value, the tangent line of something with a different tangent line. So linear approximation. Let's say you had this tangent line and you wanted to use this tangent line to estimate the slope at this point. Well, whenever you do that and the graph is concave down, you're always going to have an overestimate because you can see this slope is steeper than the actual tangent line, which would be like this, or like that. So it's the same for all estimates with a concave down shape. So if I was like here and I wanted to estimate right here, that's the actual slope. So my slope is steeper, so it's an overestimate, you know? And the opposite is true for concave up shapes. If I had a slope like this and I wanted to estimate right there, this slope is steeper than my actual slope that I used to calculate it with, so I have an underestimate. So that's just a little side note. But that is my recap of derivatives.